Hello, welcome to this video. In this one we're going to go over pattern scanning and what it actually is and how you use it. So upon researching for this video, there's a lot of, not necessarily misinformation, but when people cover this topic they generally don't cover it to death. Really good videos, really good resource in general. Look in places like Guided Hacking, they get it right. That's initially how I sort of even learned about this given topic, those sort of things like forums many years back. But a lot of recent videos I've seen haven't been covering this topic overly well, especially some longer sort of set videos that I've watched. They're not doing it wrong, but they're just not going fully in depth in greater detail with sort of how you would resolve certain issues with pattern scanning or just in general how memory works, which is their fault. It might just be they don't know and don't know any better, and fair enough. But we're going to cover some of those in that video, and hopefully you get something out of it. So starting off, what actually is pattern scanning for the uninitiated? So it's also known as array of byte or byte scanning, and all it is just looking for a selection of bytes within memory within a program basically. So if you find a unique enough pattern, which we will go over all this, the idea being if you search for a unique selection of bytes that don't exist anywhere else in that portion of memory, that's going to be where your data is going to be, where the thing you're looking for essentially. Now, it says there, for the best results, this selection of bytes must be unique and only include code and not data. As I said there, reiterating, scanning for code and not data. What do I mean by that? You're scanning for instructions, not accessing data basically. So you're not going to scan for heap memory or offsets, things like that. You're only going to go for things that absolutely don't change, basically static values. So instructions generally aren't going to change unless there is an update. So if we'll use a game, it's the easiest example. Any sort of game or any engine will get title updates every now and then. I think your favourite games, Counter-Strike, League of Legends, they all get updates. Inside of those updates there's going to be changes to the game code. In a minor update, there might be some, as I say, minor tweaks or not too many major things where things are going to have a complete revamp. So in general, if you've got a good enough selection of bytes, the actual instructions probably aren't going to change. The data will, because obviously the locations in memory have shifted. The padding and things like that, it's not going to be aligned like it once was. It's just how it works when you rebuild an application. But the instructions generally are going to remain mostly the same. Now, a major update, you might get a lot of reworks. So a lot of the time, the instructions are going to change because the actual core logic of the application, which obviously gets broken down into the machine code, has itself changed. So that is why they're going to change. We'll go over this in, obviously, as we always do, in more of a practical sense. So it's a bit easy to understand if you're not getting it. But yeah, it's not, there's nothing really to it. But for the longest time, pattern scanning sort of stumped me. And I know someone has requested a video for this, so hence why I'm covering it now. And just use pointers. So this is always a really good argument to pattern scanning for people who either don't want to learn it or just don't want to use it. And I really don't know why, because it's probably easier to pattern scan once you've found something. If you get a good enough pattern, you'll always be able to find it. Whereas if you use pointers, that's not the case. Just as I found out, I was using ID Tech, and I restarted a level, and a pointer that I'd found for my local player just reset. And this happens a lot with games. You'll find a pointer, just in every engine is different, and even in an engine that you might know quite well, trying things a different way, it's going to break. And pointers are one of those things. They are not the be all and end all and God tier. If anything, God tier will probably be your pattern scanner, and even then it's not foolproof. So many things can go wrong. But to this argument, no, flat out, no, don't just use pointers. Learn how to pattern scan, use that, use them both interchangeably as and when you need to. So it says there, all engines are built differently, and pointers cannot always be a reliable way to find location in memory. Pointers sometimes just don't work, and they will be tricky to diagnose and fix. They will give you a headache, and they will work, and then they will just stop working, and all of a sudden they'll work. And it can be nightmarish, and it's much easier if having these sort of issues just to pattern scan it. If something's really hard to find, pattern scan it. Don't use a pointer, because you'll lose it, and you will just get frustrated. With the correct pattern with the correct pattern, scanning will only find your desired location. So it's always good. If you have got the utility to use it, if you don't know how, just use pattern scanning over pointers every day of the week. So code versus data example. So just breaking down a little screenshot here of a game in Cheat Engine, obviously Assault Cube. So it says at the bottom, we want to scan for code and not data. Data is more likely and will change, whereas the code is less likely to be changed, mostly mentioned later. I've already gone over this briefly, but basically what that means is that, as you can see, the data portion of that, the relative offset, at every update, that is going to change. So as you can see in the bytes here, when we have a look, if we were to create a signature with this pattern here, we would, as soon as the game updates, our pattern would break because we've scanned for data and not code. Whereas if we scan for instructions, such as move, call, multiply, things like that, it's generally they're not going to change. They're going to change eventually, most likely, but it'll be far, far longer than when things like data changes, things like that. It's just how the nature of things work. So really quick, just to go over some common terminology for pattern scanning, so you're familiarity with it and you're aware of what these things are. So pattern itself, a sequence of bytes, usually represented as a chart array or of some sort. Sorry. So as I said, that a pattern can come in any sort of format really. Use vectors if you want. Chart array. They all decompile to the sort of the same thing. Obviously different types, but they are one of the same. Some sort of chart array, and generally you can't go wrong. So a wildcard, an identifier which indicates this byte will change and holds no set value, and it's typically represented as a question mark or a double question mark. Wildcards are also commonly used with masks, and masks are identifiers which bytes inside a pattern should be skipped, typically represented as an X or both an X and a question mark, indicating valid bytes. Denoting bytes which should be skipped. So basically what that means there is when you see an X and a question mark, the X represents valid bytes and the question mark will say the bytes that should be skipped. You'd use your masks in a combination with your pattern. Well, in some use cases you would basically put your pattern in itself and you just put in the invalid bytes, let's say as zeros, just so you're not going to forget. And then in your masks you basically say, oh, skip the zeros essentially. And we'll see examples of these in a second. It's a bit easy to understand. And finally, combo patterns. It's just like a regular pattern except the wildcards mixed in with the pattern. These are the most common that you'll probably find. Not too many things I've seen. It typically use masks anymore. A lot of tools that accept all of them in a way, but a lot of them also just use combo patterns because that's just the way it works. But I say if you're using a tool that's been developed in the last sort of 3 or 4 years, or even the last decade, they'd most likely be able to generate all the masks or combo patterns as well. So as you can see, some visual representations. So there's your pattern there. So as you can see, the valid bytes that we want are represented by actual valid bytes, and invalid bytes would be just the zeros here, so we just know to skip them. We'd insert this pattern as well as a mask. So as you can see, 2 valid bytes at the front, and the bytes we want to skip are denoted by the question marks here. So all you're going to go through our code, or our tool is just going to parse this as it's going to see these 2 valid bytes. There's 2, great. Then when it reaches the 3rd byte, it's going to go, oh, it's not valid because we've got the question mark. It's just going to skip it. Combo patterns use a combination of the 2, where the invalid bytes are just replaced with question marks, and the valid bytes are exactly that, just valid bytes. So there's nothing too complex to say about sort of terminology and types of masks you get. Just yeah, there you go. Use cases. So when would we actually pattern scan, and when would we want to pattern scan? When pointers cannot be trusted and don't work. If you've been digging out blind with an engine for a while over the game and you just cannot seem to get a pointer, or just can't seem to get them to work whenever you reload a save, or if they're just not being consistent, probably best to try and pattern scan. Extremely tedious to find locations or multi-level pointers, or just in general difficult values. If you've finally found something after hours of searching for it, create a pattern for it so you know you're never going to lose it again, or at least in that sort of moment, you can at least probably get some rest and come back to it later, and you know you've got a pattern to it so you won't going to lose it. Wanting to keep offsets updated after an update, so if you've got pointers, again it's just a matter of time for that. Whereas if you get a pattern for a location to a static pointer, things like that, you're always going to be able to find a valid pointer no matter what if you use pattern scanning. Generally better persistence across updates, minors and major updates. So as I said before, major updates will most likely alter a pattern, but it's not always guaranteed, and it's not always the major update might not affect the pattern you're using. It might affect another part of the engine, but obviously if you're going from Unreal 4 to Unreal 5, things like that, obviously completely different entities. That's just not how things work, but just as like a good example, it's just, yes, they're not the same, so they're going to be different. Okay, so I initially wrote like a little bit on the slides about certain games. So I've chose Assault Cube, which is obviously x86, and then the other one being Wolfenstein, which I'm going to get into after this. But after looking at the slides and reading them, I couldn't really understand what I was trying to convey myself, so obviously I don't expect you lot to. So all I've done is I've just decided to have a visual demonstration instead, which is far easier to understand, especially when it's stuff like memory. So we're just going to go straight into it and just sort of go over what it is I'm trying to convey. So in Assault Cube, as we've already mentioned, uses a lot of static references. So in this case, we've just found a local player. I'm not going to be covering that in this video. If you don't know how to do that, it's probably not the type of video for you. But as you can see, we've got static references to our local player here. So all I've done is I've just seen what's accessed this address, and as we can see straight away, there is a static location being pushed into the register, or what being put into the EAX register. Better yet. So if we go here, this is the instruction. It's moving a static reference into EAX. And if we look at the bytes down here, as you can see, it's in little ending. So obviously, if we want to read it, we're going to have to reverse it. So 0595404, that kind of thing. And if we just take those bytes and we put them in as an address, as you can see, it gives us a location in memory. At first glance, obviously, it might look a little bit funny, but that's because obviously it's in decimal, not hexadecimal. And as you can see there, that gives us our address to our local player. So in this case, if we wanted to find this location, we just have to pick some bytes. Okay, so after briefly forgetting how my brain actually works, then all I've done here is just created a unique pattern. So we've just found a completely unique location in memory. So I just remove these last 2 bytes here and we just go through and have a look. Or if we keep going, no, keep going. Oh, we'll start again, we'll do it again. So as you can see here, if we start off, we want to find this is the line we're choosing to start with, so this is where it's going to find. And as you can see, we've got 16,000 locations in memory that this potentially could be, so it's not very unique. Obviously, we only have 2 unique instructions and 4 bits that we're going to ignore afterwards, so we need to narrow it down a little bit. So we've obviously got the first 2 bytes here, the move instruction, and then we're going to go for another instruction, this next move after this. So once we get this, it'll narrow it down massively. And as you can see, if we take a look at our address here, our relative address, 1184FC, as you can see, this is the one we want. So we basically want to narrow this list down from 14 to 1. And how we're going to do that is going to choose a unique selection of bytes. So it's a 4-byte pointer again, which is just these bytes here. And then finally, obviously, some unique bytes here, 3, 2, and C9. The instructions, so let's put these in. And there we go, we found our unique address. Cheat Engine's really good for this. Obviously, if you've got your own code for pattern scanning, I would always recommend you use Cheat Engine, use the tools you have. If you're writing your own code, it can potentially sometimes you might be creating bugs and you misdiagnose it. Whereas if you use something like Cheat Engine, you always know you're going to find the correct addresses and the correct things, because it's far less likely that Cheat Engine is going to be wrong rather than your code. So that's what I would do. I always test in here first, create a pattern, and then see when I get a unique address like this, and then I will use it in code, because then I can obviously debug things a lot easier. And then from this, we can use a thing like offsetting. So obviously, if we're starting here, and we want to get to our bytes here, so we need to go from FC to 02. So we're just going to add probably 4 bytes, and that'll get us to where we want to be. And then +4, 5900. Where's that taking us? A little bit too much, so 2 bytes potentially. 2 F053, where does that put us? F0539. Oh, sorry, my bad. We've gone too far, so we'll go 6 bytes ahead. A10459. There we go. So once we've added the 6 bytes, which is obviously accounting for the instructions here, and then obviously the extra 2 bytes, we're going to be on we're using offset to basically reach our desired pattern, which is another thing you can use. You don't have to go specifically on certain instructions. So all I've done here is we could have started on this line here, so we could have used this instruction and just gone back down and we would have got the same thing. So we can do that. We'll do that in a second actually. And we're just showing another way off there. You can use offsets as well, just like you would if you typically use an offset, just another relative location in memory. So that's all we're going to do. We're going to get a pattern from somewhere, and then once we find that predetermined location in memory, we know that from that point, this is going to be here. Obviously, with offsets, with patterns in general, if things have a major update and things do change, that offset is obviously not going to work. So that's something just to be aware of. That's why I always prefer getting patterns. But obviously, using offsets wherever needed, it's not particularly a bad thing. It's just another way to do it. So if we just wanted to go straight for this and we just wanted to fob this next pattern off, we could just go something like this. So for instance, A1, and then we're just going to ignore these bytes. We're going to go 3, 2, C9, and this would probably be pretty unique. So A1, 3, 2, C9. Oh, apologies. There we go. 1, 2, 3, 4. New scan. There we go. We've got 5 locations in memory. All I've done there is obviously I forgot to not include the 4 bytes after it, so it found another location in memory that was incorrect. So now we're just going to go for this one. If we put 8815 in there, and we're definitely probably going to have that unique location in memory. Oh no, we're not. 8 C9. Let's try again. Oh, 8B, my mistake. 8B. Next scan. There we go. As you can see, we've found our location memory where we want to be. 88502. Here we go. So obviously, if we read from here, we're gonna have the bytes that we want there. Another thing to be aware of with patterns and things like that. If you create a pattern that is obviously very unique, so let's say if we wanted to get a location in memory, if we just chose, let's say, all these instructions up until this point here, so now it's a massive portion. If you create a massive pattern, there's more likely it's going to change. The smaller your pattern is, generally the better, but obviously you've got to be careful that in case that small portion of code does change, you're going to have no idea where it is. Whereas if you use a larger pattern, you essentially get a more unique location in memory. So things potentially might change, but other things aren't, so it's still going to locate where it is. Where if you choose that very small bit, if even one thing's incorrect, it's going to have no idea. But it's like to sort of use what you think's appropriate. See certain things, how they work and things like that. Just go with what you know. Because obviously there's use cases for both. So if you were to choose a really large pattern for one instance, then potentially it could break. Whereas if you choose a smaller pattern, it's probably not going to work as well. Things like that. It's just things to consider. But now we'll show it in the x64 process, which is obviously Wolfenstein. Okay, so now back to the slides. This is initially what the Assault Cube demo was going to be. We're going to go over slides and then go over the game. But as I already said, I just couldn't make any sort of sense of it. This one's a lot better made. So we're still going to go over this, then we'll go over a game as well. So all I'm describing here is just my process of obviously elimination, how I've found certain things in the game and how I've gotten to where we are. So all I've done is found the health of our local player, and then we've found the local player actor object. Obviously in a lot of these, every game engine is different. A lot of modern game engines will use a lot of inheritance and object-oriented principles. And if you're not familiar with it, it can be a bit of a nightmare in memory. So if it's your first time, I probably wouldn't recommend starting on an engine like this, which isn't really that bad, especially compared to other engines like Unreal or Call of Duty. But it is just something to be aware of. Now, if in case you wasn't aware, these are all COD, Doom. They're all sort of built on the very core, a very similar engine, the Doom engine. This is what the ID Tech engine is as well. So yeah, just a little bit of trivia for you there. So all we've done here is found the health, then we found the local player actor object. We searched for local player address, and then we found the entity list from that, and that was from looking in reclass. That was by pure luck. I had nearly missed it, but then we found it. So it was a bit of a pain, and as I already said as well, as I already alluded to, this game was a bit of a nightmare with pointers. So straight away it made sense to use pattern scanning, and it obviously just happened to line up nice with the video, so that's why I've used it. So as you can see here, we've just sort of found what's going to be accessing this address here. So if we go for our entity list, and we've just gone, we've had a look, so we want to create a pattern for that, and we've done exactly that. We've found a pattern and a location in memory there. We've obviously found our unique pattern, and that's taken us exactly where we want to go here. So a little bit of engine background. It uses a static pointer for accessing the game base class. So the game base class is where we can, if we find something like this in an engine, we can access anything from that class essentially. So we can use the base class to access our local player, and then we can access the entity list, things like that. So in this case, the entity list, well, we found the entity list from the base class, and then in the entity list at the index 0 is our local player. So it gives us essentially everything we need, and we can sort of work off that. It's a really good starting point. And it also just happens that, obviously, as I said, it uses a static location in memory, which is obviously really good and always brilliant for us. So all I've done is I've put a breakpoint on that static location, on the base class, and we're just sort of finding out sort of where things go. And initially, you see a lot of reads, and when you try and do things in game, there's not a great deal of things being accessed. So as you can see from this from the registers, the offset 1D0 is where we're going to, but we want a more static location in memory. As you can see, we found here. So upon reloading the game, we found exactly that. This address here is getting moved into R12, and this is like something that's going to pique your interest. This is something you want to look for and dig in deeper too. So as you can see, after looking at the bytes, we go straight in there. It's not as easy as our address just isn't being put into the register. As you can see, the bytes don't quite line up, and this is typically where a lot of people who are new to pattern scanning or memory in general, especially pasters, are going to look at it and just go, oh well, the paste is ruined, nothing's lining up, what is happening, what is going on. As you can see, the bytes and the opcodes are a little different, and in this case, it's not just because the instructions. Obviously, certain instructions can have different. The same instruction can have different bytes. So, for instance, the jump instruction's got about 5 different relative, near, and absolute long jumps, things like that. It's just one example for you. You can go look it up on NASM, things like that. There's no static offset we can just read, so the paste is basically ruined. We're just going to have to give up and just, I don't know, just do whatever, but our pattern scanning career is over. So, yeah, what do we do essentially? How do we get around something like this? This is typically where a lot of videos will sort of give up as well. They'll just say, oh, go here, read this, and then you can read it with your eyes, but we don't want to do that. We want to automate the whole process, so we're going to have to understand how things work, which is obviously a paster's worst nightmare. So what this concept actually is, it's x64 RIP relative addressing, and this happens a lot in x64. It can happen in x86 too, but it is very common in x64. Basically, the reason why it is used, it allows us to access memory within a 32-bit address space within that 2 GB region. As we know, 64 bits extends that region, so potentially if something's so far away in memory, we won't be able to reach it through a near jump. But in x64, we can do exactly that, and it's achieved generally through RIP relative addressing. In this case, a common accessing method known as RIP relative addressing has been used, and it uses the current instruction pointer, the RIP as we know, to locate memory with a relative offset. To find the address storing our base pointer, we must do some math. Not ideal, no one likes maths, especially me. I'm sort of foreign to it, so it takes me a minute sometimes to do even basic addition or something like that. It's not my favourite thing, but in this case it's not too bad. So as you can see how I've sort of gone about finding the location in memory we want. So started out, we want to get the RIP to the current location where this is going to be executed. So as we can see here, if we go through, this is going to be the RIP. The RIP is going to be executed on this instruction here, and this instruction is stored at this, or it's mapped into this location in memory here, 148F41. So we need to get our base address of the module, and then we need to go to that location. So that's all we're doing here. We're calculating the starting point of the RIP here, this line now. And then we're adding the relative offset from the move instruction, and it's in little endian format, so it's in reverse, going to look a little bit different to the bytes there. Little endian there, and this is obviously how we've displayed to ourselves here. It's not 32, well, this doesn't really matter in this case, but this is the matter of, this is the size of the instruction, so just ignore that. This is the size of the instruction, so in this case, there's been 7 bytes that's been used, so obviously the difference between 1 and 87, and if you count the bytes there, 1, 2, 3, 4, 5, 6, 7. There is 7 bytes that have been used, so that's why we want to use that, the size of the instruction. And if we've done our maths right, we will get the location in memory that we want. And this happens to be the location of the base class. So stored at this location in memory is the x86 address of our base class. We'll go over this now, but I'll show you this in a visual format so you can see it. But that is the correct location of our base class in memory, at least it was. So the actual math for doing that in the IDTech 5 engine, this can differ. Obviously, different engines use slightly different things. Some of them might be 32-bit line, things like that. But generally, this is what you're going to use. You're going to go from the RIP location plus the relative offset, and then plus the instruction size. So obviously, as I said, in our case, it was 7 bytes, but that's going to change, and that will give you the destination address of where you want to be. Okay, so right now in game Wolfenstein, we're just going to go over what we've just talked about. So as you can see, we've got the base class somewhere. I believe this is the local class here. It'll lag a little bit when we attach the debugger to it. Find what axis is the pointer. Yeah, this is the one. So once we restart the checkpoint, we are going to see things change on here, which is exactly what we want. There we go. I'm just going to stop that because it absolutely lags living out the game. As you can see here, our static location has been pushed or moved into the R12 register. I need to stop saying push, that's incorrect. As you can see as well, the bytes do not look the same, so we see our offsets here, 161EE70. There's no such static offset being made here, but as we've already talked about, this is our relative addressing, and all Cheat Engine will do is just assemble this for us here, hence why it's given us this address. So obviously once we go to this address, which is the one we just discussed, we're going to see our address for the base class here, 597AA050. So if we take this address here, let's say we go into memory view here, ID game local, there we go, game base class. Nothing really to it, but that is sort of how you want to go about. If you're writing some code for it, so relative addressing, or you can either, you'll need to read this location. Obviously, we create a pattern for here, and we would find this location in memory, and then we would read these bytes here. So then we would just obviously do our maths that we've just done, and then all we'd have to do is read the address of the final calculation, and that is where we would get the address of our base class, things like that. And hopefully that's made sense to you. So that's all for this video. Thank you so much for watching. Hopefully you've got something from it. This is a no code video. I'm going to be going over the code for pattern scanning in another video. I'm not too sure when that will be, but hopefully a little bit after this one. But yeah, hopefully you've got something from that, and it's nice and short and sweet. So anything you didn't understand, it's sort of in that time frame, you can go back and look at it and have a more thorough understanding of it. If there's anything I didn't cover as well as you thought, or something you're a bit confused with, please leave a comment, as someone did, hence why this video is being made for them. But hopefully you've got something out of it and you now understand the sort of basic concepts, and you can work with it a bit better for you. Thank you so much. Stay tuned for the next set of videos.